The show that reveals how extraordinary items in our world are designed, constructed and produced. See the engineering, the technology and big ideas that make the world go round. Find out how it works. Coming up in today's show, how tools are forged for green-fingered gardeners managing marigolds and marrows, what to do with toxic waste, can a hole more than half a kilometre below the ground help to bury this long-term problem, and from toxic waste to noxious waste, we reveal the spillage-stopping secrets behind nappies. But first, arrive at work, unlock the door, turn on the lights. Offices all over Britain use fluorescent lighting because it's cheaper and more efficient in the long run. But how does a tube full of gas light up your life? Fluorescent light bulbs start off as a large lump of hot glass. In this fluid state, the glass can be stretched and blown into a very long tube. Diamond-tipped cutters then trim the long tube down to 2-meter lengths. Occasionally the tubes break, but they're discarded and recycled. The next step is to trim the ends. Flames burning at 700 degrees Celsius create a neat fracture line, and a tiny cutter knocks the uneven ends away. Sharp edges are rounded off, and the tubes are now ready to hold the various elements that will generate light. Fluorescent bulbs are more efficient than ordinary light bulbs, making them cheaper to use and therefore more attractive to businesses. But for that economical light to glow, the inside of the tubes must be coated with phosphor, a chemical that will cause the bulb to fluoresce. Next, the internal workings of the bulb are constructed. Like an ordinary light bulb, the fluorescent tube also contains a filament, which carries an electrical charge. This filament must be put together so it can be fitted inside the phosphor-coated tube. Fluorescent bulbs work by exciting particles of gas with electricity. These particles then emit energy which can be turned into light. Once constructed, the filaments are sealed into the tubes. Now, you may have noticed a glass tube sticking out of the end of each of the larger tubes. This is where the energy-emitting gas will be injected. The gas is made out of mercury, a toxic liquid metal used in a range of everyday objects from batteries to hospital thermometers. Mercury is recycled from these items and collected in a facility like this one. It's a dangerous process and the scientists have to be careful. While handling mercury is a hazardous job that requires a gas mask, the liquid metal can be collected in an ordinary bucket, and a simple trick using water keeps it safe. Mercury vapor is the gas that creates light in the fluorescent tubes, but it's dangerous if inhaled in large quantities. Storing mercury beneath a layer of water stops it vaporizing. Now, if you're worried about the gas in the tubes, don't panic. The amounts used in fluorescent lighting are so small they are not considered very dangerous. The bulbs are now ready to be injected with the mercury vapor. The tubes and mercury are loaded into the filling machine. The mercury is heated, which vaporizes it, and this is injected into the tubes. The heat causes the gas to release energy, and this makes the bulbs glow, even though they're not connected to a power supply. So how do electricity, mercury gas, and the phosphor coating create fluorescent light? We already know that there are filaments inside the gas-filled tube. They send out electrons from one end to the other which strike the gas particles floating in between. This excites the gas, which in turn emits radiation. But radiation is invisible. And that's where the phosphor coating becomes important. It wasn't to colour the tube. The phosphor fluoresces or glows when bombarded with radiation, and this glow is what lights your office. With the insides now phosphor-coated, filament-fitted and gas-filled, all the tubes need are the external caps so they can be fitted into lamp holders. The caps are carefully fed over the filaments, sealed into place, and the job is done. Finally, the bulbs are passed through a tester where any that don't work can be spotted before they're sent out to the stores. Although streetlights were originally powered with gas, the emissions probably wouldn't pass modern standards. But today we can still see, thanks to cleaner, greener, gas-powered technology, the fluorescent light. The English are famous for the love of their country garden. So it's little surprise that in 2003 we bought and sold over 4 million spades and shovels. They're simple tools, but have you ever stopped to wonder how a rake or even a shovel is put together? Working the land is a tough job, so garden tools need to be equally tough to cope. That's why here at the factory production starts with large sheets of steel. These are cut to shape using a rather unusual knife that doesn't have a metal blade at all. Instead, it cuts the steel using a high-pressure jet of water. Next, the steel blanks will be fired in this furnace. The burning coal leaves carbon deposits on the steel, which makes it harder and more robust. This will produce a good quality hand-forged shovel. Once it's been toughened, it's time for a beating. With around 30 blows from his 80-kilogram hammer, the engineer shapes the blade of the shovel. Once the large hammer has done the heavy-duty work, a lighter hammer is used to smooth out any dents. The blade is then returned to the fire for more hardening. This process is repeated a couple of times until the engineer is satisfied. The next step trims the blade down. The hammering process has spread the metal out of shape, so the blade is marked and cut down to a standard size. And finally, the finished blade is returned to the fire. The engineer will heat the shovel head, scrape it clean, and place it in the press. Here it will be given its characteristic shape, using 120 tons of pressure. Next, the welder will add the socket. This is a piece of metal made of softer steel, which acts as a shock absorber, damping the impact of heavy blows. It's also got a useful hole where the handle will be attached later. All of the work has left the blades a little dirty, so they're rinsed in soap and sent to an ultrasound bath. Sound waves will shake loose any unwanted dirt. The new shovel blade now gets some cosmetic work to make it ready for shop shelves and to improve performance. Here it's being sharpened. This will save the gardener some effort when working an old bed of roses in tough soil. Back in the furnace room, the engineer is hardening more steel, but this will be used to make rakes instead of shovels. This time, the engineer is hardening pre-formed bars. These will be used to form the rake's tines or prongs. Using a different press, he will crush each bar so the end resembles a point. But this process leaves extra metal attached to the tips. Using a guillotine, he can now trim away the excess, giving the tines sharp points perfect for a rake. Then they are sharpened even further, which will help the dedicated gardener to do his job more easily. Finally, the points are cut to length. A dedicated press will cut the spike from the end of the bar. It takes 8 of these carefully prepared tines to make a new rake head. They're mounted in a special vise that will hold them all in line, but there's no robotic welder here. Handmade tools require more time, effort, and expertise. Next, a socket is attached and welded into place for the handle. And now the rake is bent into shape, which will make raking up all those leaves so much easier. When all the heads have been completed, whether for a shovel, a rake, or even a pitchfork, they're sent to the handle department. High-quality woods like ash or cherry are used to make a strong handle that won't crack under pressure. The wooden shaft is fitted to the socket and checked. If it isn't straight, it won't be up to the job. The two parts are then fitted into a vise, hammered together and screwed up tightly. For the shovel, a stronger handle is needed to cope with heavier work. A pressurized vise squeezes the blade and handle together, and the two parts are riveted for extra strength. So, whether you're raking leaves in the autumn or shoveling fresh compost in the spring, a well-made garden tool is a must. Still to come, we'll find out why disposal experts are going underground to keep us safe from toxic waste, and how to keep mum, dad and baby happy, the surprising secret ingredient that makes disposable nappies indispensable. This lift goes almost half a kilometre underground. When the doors open, you have a long drive ahead of you. But what is at the end of this subterranean journey? This is where you'll find the vault that stores all the toxic waste that's just too dangerous to leave lying around on the surface. Dumps like these contain industrial waste that could contaminate land and water if left above ground. Everything from heavy metals to poisonous chemicals is stored here. This story begins in Saxony-Anhalt in Germany, where potash is extracted from underground mines. Potash is used as a fertilizer, and the mining process has two benefits. Firstly, the potash, secondly, the large holes it leaves behind. The potash was laid down millions of years ago. As an inland sea evaporated, it left layers of mineral deposits. Today, these layers are found deep underground. Mining the potash is a simple process. Drills are used to prepare holes ready for the industrial explosives which are inserted. The mine will then be evacuated and the explosives detonated. When the dust has settled, the miners will head back to the face with big tractors. They scoop up the loose potash and it's sent above ground to be processed into fertilizer. When the mining's done, the toxic waste arrives. It too will be processed, ready to be stored far below ground in the hole where the potash used to be. This load is arsenic, which can be very hazardous to people's health. Before it's buried, it's sent to the lab to be tested. Scientists check there is no liquid mixed in with the waste. Any leakage could be disastrous. The next test is for gases, so a protective mask is needed before opening the bag. The buildup of certain gases in the waste could cause explosions, yet another danger factor in the storage of toxic waste products. Once checked and cleared, the arsenic is ready to be stored in the dump deep below ground. But before it's sent off, there's one last thing to do. The scientist takes a sample. The reason why will become clear down in the mine itself. Loaded into large containers, the arsenic is taken underground. With the waste heading for its final resting place, the scientist takes his sample to a kind of underground library. This is the records department, but instead of books, these jars contain a sample of every waste product stored down here. The storage system acts like a map, so the scientists know what kind of waste is stored and where to find it. He adds the sample from the latest batch of arsenic to the end of the line. Meanwhile, the dump is being carefully prepared for its impending delivery. First, any loose material is removed from the ceiling. Rockfalls might rupture the specially sealed containers. Next, the workers will drill holes in the ceiling and bolt in special reinforcing steel rods. This will act as a further layer of protection to prevent the roof collapsing. The rods penetrate about 1.2 meters into layers of solid rock. Once they're firmly fitted into place, the rod ends splay out like wall plugs, gripping into the solid rock layer to stabilize material in the loose layer. This extra reinforcement can help support around 14 tons of rock in an 80-centimeter diameter around the rod. The mine contains several million of these helpful reinforcements already. As well as the ceiling, the floor is also being prepared. Special vehicles flatten the loose rubble into a stable road so that the toxic waste transporter can come and go safely. There are hundreds of kilometers of roads throughout this mine, and it is possible to get lost if you don't know your way around. With the ceiling stabilized and the road prepared, the waste can now be brought in. Special tractors pick up the bags, keeping human contact to a minimum. Often a byproduct of modern industry, toxic waste is an increasing problem, and one solution is to bury it deep underground, in this case where the potash used to be. The joy of parenthood, that time of life when you have a little one to look after. But there's one part of child rearing that few relish: nappy changing. Salvation has come with the invention of the modern disposable nappy, but there's much more to making this innovation than meets the eye. Pulp is used to form part of the core of the nappy, and you may be surprised to learn that this pulp is made out of pine wood. As well as the wood, these workers are adding gigantic bales of cotton wool. This is grown in the USA, and together with the pine fluff will be combined to form the soft core of the new nappy. The nappy cores are made inside this machine. Here, the pulp and cotton wool are mixed together and shot out the other side, ready to be woven into strips. What emerges is one long strip of pulp, but the guillotine on this revolving drum will cut it into more nappy-sized pieces. The next addition is the outer plastic. This waterproof layer will act as a final barrier to stop any seepage from spoiling baby's clothes or anything else. However, the real protection in the modern disposable nappy comes from this granulated chemical. This is sodium polyacrylate, and it's the superabsorbent secret that stops spills. As the granules absorb the water, they swell and become a gel which locks the liquid into place. The disposable nappy industry is big business, so companies are continually developing these kinds of products for the market. The nappy on the left here doesn't have a superabsorbent gel core. The one on the right does. This test shows the gel's dual benefits. First, as you can see, the gel cored nappy on the right absorbs the liquid far faster. Second, the leakage test shows that when a dry napkin is applied to the first nappy, there's clear leakage from the absorbent part. However, when the same test is conducted on the gel core variety, there's almost no leakage at all. The chemical has done its job and trapped all the liquid inside. The superabsorbent core is layered between two sheets of the soft pulp we saw earlier. Next, a fleece will be added. It's made out of a cloth similar to Gore-Tex. This will help keep the baby comfortable, allowing his or her skin to breathe. With all the layers in place, the nappy can now be shaped. Indentations for the legs are cut out, and the computer checks each one to make sure it's been cut in the right place. Sometimes the cutter gets out of sync, but the computer is quick to identify the problem nappies, and they're removed from the line straight away. The modern disposable nappy has come a long way since the first prototypes were invented in the 1960s, but there are concerns that the millions used and dumped in landfills every day may create a big environmental problem. Public opinion is beginning to turn back towards the reusable nappy, but current figures show that 90% of UK parents still prefer the convenient disposable variety. The final stage of the production process sees the nappies being counted, squeezed down to remove any air, and packed up ready to be sent to the stores. The most important role of the nappy is to keep its contents inside. However, the baby's comfort is also vital. Nappy rash causes grief for both babies and parents, but the gel core may help to reduce the problem. Tests show that when overall skin dampness is reduced, so is the incidence of nappy rash. And while they may be causing a mountain of waste, most parents won't do without disposable nappies.